Hello, in this video we will look how to differentiate the product and the quotient of two functions. We did learn the limit definition of the derivative, and we know that occasionally if the function is more complex, the process is quite long. It means the point is to find some formulas, some shortcuts to get the derivative of the function. We can start just looking again at the constant function. We of course know the derivative of the constant function is basically 0 because constant function is represented by the horizontal line. The slope of the horizontal line is 0. And we learned that the slope of the line is the derivative. I also use the definition. Limit as h goes to 0, f of x plus h minus f of x over h. Value of the function is always c, constant. 0, c minus c is 0, 0 over h. H is still tiny number, it's not 0. That means the value is real, 0, and it is proven that it's 0. Perfect. Constant function, derivative is 0. Now, that's a nice Leibniz notation. D of the constant derivative of the constant function with respect to x is 0. Okay, we also learned that formula, but I'm just trying to look at this again. Power function, x to the power of n. If at the moment when n is positive, and we did use the definition, and what we've got, derivative of x is 1. We don't even have to use the definition for x because slope of the f of x equals to x is 1, and that's the derivative, that's the rate of change. X squared, since parabola is changing, it's not a constant change, then we use the definition, limit definition, and we've got 2x. Then we also use the x cube, we got 3x squared. We didn't, I believe we didn't do the x to the power of 4. However, looking at the numbers and the outcomes above, we may figure out the pattern. If the exponent was 3, 2, 1 respectively, then it becomes a coefficient and the original exponent, original power is decreased by 1. Then we will have 4x cubed. And then in general, x to the power of n, it will be, I can write down n, x to the power of n minus 1. This is the power for the differentiation. And from now on, if it's not specified, we can use the formula. We don't have to use the limit definition. And I have the power rule, general version. Any function, I mean x to the power of n, and n could be actually any real number. Yes, any real number. Then the derivative can be computed this way. I mean, for the proper power function, n is positive number. Yes, x to the power of 1, 2, 3, 4, or fraction. But for instance, when we have to differentiate 1 over x, looks like a rational function and looks actually like the new rule that we will actually cover in a few seconds. The quotient is the quotient of two functions, 1 over x. But what we can do, since we still don't know, we may rewrite in the power form, x to the power of negative 1. Okay, and then we will say negative 1, x to the power of negative 1 minus 1 is negative 2. And rewriting without the negative exponent, that's the formula, that's the function, that's the derivative, negative 1 over x squared. Also, we may have, for instance, root function. Yeah, I can also rewrite this in the power form, x to the power of 1/2, and use the above formula. 1/2 will be placed in front, and we subtracting 1. 1/2 x to the power of negative half, and negative half is the square root in the denominator of the quantity x. We will always try to rewrite expression without a negative exponent. Okay, now Yeah, like for instance, I have an example here just to practice. We don't know because we might need different rules, but we can rewrite nicely this function cube root of x squared in the power form, and then directly applying the formula 2/3 x to the power of negative 1/3. And we can rewrite without the negative exponent cube root of x in the denominator. Oh, too fast. Also, this question is asking for the domain. That means we may notice cube root of x x squared, actually even better, can take any real numbers. However, the domain of the derivative will be also all of the real numbers, but we have to exclude 0 since we end up having x in the denominator. So this is for the derivative. This, the top, all of the values are for the function. That sometimes could happen. Function, basically derivative is not defined at 0. Since function is continuous function, we have something going on at 0. And we actually know this graph from pre-calculus. Cube root of x squared looks like this. And we may notice at 0, we have these sharp corners. When we have sharp corners, no derivatives. Derivative at 0 is undefined, but we can see this based on the domain. Okay, just a quick review. And now let's look also at this constant multiple rule when we have to differentiate constant times the function. Yeah? That's a little bit different than just the constant, because constant function is constant, is horizontal line, derivative is 0. But when we have this combination, we may put the constant outside and just focus on differentiating a function and then multiply the outcome with the constant. And that means that's different. Constant in this case is not 0, derivative of the constant, because it's not just a constant. Like for instance, let's say 2x. What is the derivative with respect? We know right away that is 2, but I can put 2 outside and I can just focus on differentiating a function which derivative of x is 1, it's 2. That's basically, we will apply automatically, but that's the rule. For instance, I have this 5x squared over 3. Then we can think again, it's like a quotient. Shall I apply the new rule, which we will learn in a minute? But then we can see, okay, this is just the constant. Let's separate the constant and differentiate just the main function, main variable. 5/3 times 2x. Of course, 10x over 3. Okay. And we also have a sum and the difference rule. Derivative of the sum of two functions is sum of two derivatives. Derivative of the difference of two functions is the difference of two derivatives, assuming that both of them are differentiable functions. Derivative exists. Okay. And what I have like a nice example, but don't get scared. Let's look at this function. I just type this. Having like a practice and experience, I know that all of my students will give me this answer right away. Right away, not even thinking that we using step by step all of the rules. Like we will differentiate, it's the addition and subtraction, is the polynomial. That's mean derivative of addition and subtraction of the function is the addition subtraction of the derivatives. So we can see derivative, derivative, derivative of each component. And then, for instance, 12x to the power of 5, I use the constant multiple. I kept the 12 outside and just differentiate x to the power of 5 and then multiply. So don't worry, you may skip all of these steps. You can just jump and provide the final line. Okay, but now the point of this session is to find another rule for the let's start with the product. And we may, when we will think about the rules that we just learned, the difference I mean the addition, the sum rule, the difference rule, we may guess wrong at first. And let's see, we have to figure out. So for instance, if I will take a product of two functions, f of x times g of x, and I just pick the easy function, x times x squared, yeah, we may think that we can just derivative of the product will be product of their derivatives. Yeah? But you see my question mark. That's still, we're not sure. But let's see, derivative of x and derivative of x squared. Derivative of x is 1, x squared is 2x. When I multiply, is 2x. Yeah? Now, having this type of product, it's not a problem because we may avoid the product right away. And that's what we will actually do. When we have the option algebraically to combine these two functions, avoid the product, we will do it. And we will, of course, write x cubed, and derivative of x cubed is 3x squared. That means this is the correct answer. That's not the correct answer. Okay, 2x is wrong. And just the conclusion for now, derivative of the product is not a product of two derivatives. Okay, we have to find a new formula, and I have the formula. We will look a little closer. Yeah? But of course, in this case, we were able, but if we will get a function like a product of two different functions, two different types, yeah, like let's say x times sine of x, we cannot combine them. So we cannot just say, oh, derivative of that product will be derivative of x times derivative of sine of x. No, that will be wrong. Yeah, we have to, from now on, we have to pay attention. Okay, let's find out how we can differentiate, for instance, function like this. I use the limit definition, but don't worry, you don't have to know exactly how to follow. I mean, you can follow this proof, but we have to just find out the final formula. That's when we will take a product, f times g, and I can set up the limit definition. Limit as h goes to 0, f of x plus h minus f of x over h. Then I substituted to the function, like I evaluated for x plus h and for x. And then I did a couple of steps, like I add and subtract a term, but that's how we do when we have to prove something. And then I split for two limits. And you may notice what I'm getting. I'm getting at the end, let's look at that line, I'm getting limit, limit of, I didn't explain that line, but you can check what I did. I just split for two limits, keeping half of the terms for that part and the half for this part. Okay, limit of f of x plus h, if h is 0, is f of x. That limit, you can probably realize that is just the derivative of the function g prime of x. And then addition, function g of x, the limit, it's constant with respect to h because it's no h, then I can copy limit of the constant is a constant. And another component, another actually factor is limit, which represents f prime. That's what we have to do. We have to just take this final line. Derivative of the product, f of x times g of x, will be equal to this. F of x times g prime of x plus the other way, g of x times f prime of x. Okay, that means that's the derivative. And I have this, I just have this nice table, nice rule, and that's the rule that we will use it, okay? F of x times g of x, derivative with respect to x, and we will follow this. I kind of switch this because it will be helpful for the next rule, quotient rule. I started with f prime, that's we have to differentiate the first function times the second without changes, and then plus f of x, original function f of x, times derivative of the second function. Okay? And we may quickly prove, like what we had. We had x and x squared. We know that this is x cubed. We know that the final answer is 3x squared. But let's apply the product rule. Derivative, first of all, we will differentiate x times the second function, x squared. And then we will copy first function and we will differentiate x squared. Derivative of x is 1 times x squared. Derivative of x squared is 2x. And then we have x squared plus, oh, hang on, derivative of x squared is 2x. 2x times x, that's what I was thinking, is x squared, and the final answer is 3x squared. I mean, definitely this formula works. And again, in this easy product of the same type of function, we will not even apply. We will say right away. But if we have complicated function that we cannot combine them together, different types of the function, we will follow that rule. And when you will practice, this formula will be like a second nature. You will never make the mistake. Okay. And I have the proof for more complicated, like 6x cubed times 7x to the power of 4. When we combine this, we have 42 times x to the power of 7. Yeah, that's mean I'm avoiding that product because I'm able to do this. And then 42 times 7x to the power of 6, 42 times 7, we can take a little bit of time and get 294 x to the power of 6 done. But if I would like to apply the product rule, I will differentiate the first function times the second, plus first function times the derivative of the second. And the answer is the same. Okay, I have another example, like for instance, this one. What's the derivative of the function e to the x times x to the power of 4? Yeah, please do not just differentiate term and another term, like factor another, because this is the thing, the dot, the product is never like printed. So we have to figure out that this product, we have to realize that this product, and then differentiate. Derivative of e to the x is just e to the x times the second function. Now copy the first function times derivative of the second function for x cubed. Done. I might factor out x to the power of 3 e to the power of x. Okay, that means when we factor out this, we will have x stays plus 4. Okay, it's a nice product form, but this is the rule. I know that you will practice and you will get this. Okay, and now what about the last rule, the quotient rule? How we can differentiate f of x over g of x? We may guess that it's not derivative of the quotient is not the quotient of two derivatives, respectively f and g. But what I will do, we can also use the limit definition, and it will be a little bit longer process. We can do it, but now I can take the advantage of the product, okay? And I will use the product rule. Just to clarify, we're looking for the derivative f prime of q. That's we're looking for the formula, how we can differentiate q of x, which is defined as a quotient. Let's see what I did. I have my proof on my other slide. Okay. Now I'm just proving, that this is not derivative of this is not the derivative of, the quotient of two derivatives. Okay, I took x cubed over x squared. When we simplify this, we will get x, correct? We will get x, and derivative of x is 1, done. But what I was trying to do, I was trying to differentiate the top and the bottom. Yes, like the derivative, trying to think that the derivative of the quotient is the quotient of two derivatives. Okay, we have 3x squared on the top, 2x and the bottom. When we simplify, we will get 3/2 of x, which of course is not correct. because this is just x, derivative is 1. That's the correct answer. And then, then this is the conclusion. I was trying to just saying quickly, but that's the conclusion. Derivative of the quotient is not the quotient of two derivatives. Now, let's see. Now I have my proof that I will use the product. We're looking for the formula. Let's uncover what q prime of x is equal to. What I did, I multiply both sides of this equation by g of x. Basically cross multiply, because this is cancel out and I've got this. F of x equals to q of x times g of x. Now I can differentiate f of x because I have product on the right hand side and we know the rule. That's the notation, derivative with respect to x of the left and derivative of respect to x of the right hand side. This is just f prime. Okay, this one, it's a product rule, q prime g, q g prime addition. Now we may notice that we suddenly have q prime of x. That's what we're looking for. Let's solve this equation for q prime of x. I will subtract that part from both sides and divide both sides by g of x to isolate q. You can do it. It's just the algebra, q prime of x. Okay, we almost there. We have f prime, we have g prime, we have g of x, but we also have q of x. What we will do, because we want everything in terms of f and g, I will substitute instead of q of x, f of x over g of x. Okay, and just simplifying this, I will multiply each term in that fraction by g of x. G of x times f prime. When I multiply by g of x that part, g of x is cancelled out, f of x will stay times g prime, and g of x times denominator, it will be g of x squared. And actually, that's the formula for the quotient rule. In order to differentiate the quotient of two functions, we will follow this. We will differentiate f of f prime, the first function, the top function, times denominator, function from the denominator, minus f of x times g prime. You may notice the top of this fraction looks almost the same like a product, however, is minus subtraction. But we have to start with f prime g, f g prime. And then denominator squared. Function that was in the denominator will stay the same, but we will just square it. Okay, that's the formula. Okay, and that's the rule. And please, from now on, when you have the quotient, you will use it. If you can avoid the quotient, we will avoid it. But if we are not allowed to avoid, like for instance, let's say e to the x over x squared. It's not possible to avoid this quotient. And we would like to differentiate. Let's do. Derivative of e to the x is e to the x times function from the denominator minus e to the x, yes, as a function from the numerator, times derivative of the denominator, and then denominator squared. Again, we can factor out x, e to the x. We will have x minus 2. And this will be x to the power of 4. And we can simplify, but the first step is important. That's the derivative. Okay. And we almost done. Oh, of course, the quotient. You can read the words, description. And I do have this function. Yeah? That's what I said. Even if this almost the same type of function, in order to find the derivative, we may use the quotient rule. But since we have one item, one expression in the denominator, we can divide. We can avoid the quotient. 3x squared over x and 2 root x over x. This is just 3x. And this is x to the power of 1/2. This is x to the power of 1. And we're subtracting when we divide. And now this is the derivative. Derivative of 3x is 3. Derivative of this is this. And that's done. The only thing, just to be consistent, we will rewrite without the negative exponent, square root of x cubed. Just the negative exponents may be confusing. In order to use the derivative for the later application, it's much better to do this way. Okay, and I think, oh yes, I have similar that we just did. Maybe I can change. Let me put ln of x. I don't know if we remember derivative of natural log of x, but let's try. That's what is the derivative of natural log of x over x cubed. Derivative of natural log of x is 1 over x times x cubed minus natural log of x times derivative of x cubed, 3x squared, and denominator squared. Let's have the final form. 1 over x times x cubed is this, and this one, of course, we're not combining because that's, and this will be x to the power of 6. We may, look at this, we may factor out x squared, 1 minus 3 ln of x. And okay, I can write this way, 1 minus 3 ln of x, and we may subtract 4. Yeah, then we subtract, we canceling out 2 of these x's, 4 will stay. Okay, that's really nice form. And that's the derivative. That's, we can see it's not just derivative of the numerator divided by the derivative of the denominator. No. We have to follow the quotient rule. Okay. That's all of the formulas so far. Constant function, power form, constant multiple, addition, subtraction, and the new rule that we just learned today, product and the quotient. Okay. In the next session, we will practice all of them intensively. Thank you.